I'm definitely off a little bit, right? So let's come over here and let's put a, I've got 2 hydrogens, and somehow I need to kind of change it up. I can change this hydrogens, and I apologize because here's my hydrogen over here. But let's look. H2O. H-H-O. This one. H-H and an OH. So I actually have 3 hydrogens and I have 2 hydrogens. So I'm not even at all. Okay? I'm not balanced. Even though this looks like it's balanced, that was my fault for writing that down. So I apologize. Because I do have water and then I have a polyatomic on this side over here and they're separate, then it's easier for me myself to look at it broken apart. I have 1 H2O molecule, which means 2 hydrogens and 1 oxygen. On this side, I have 1 OH hydroxide and I have 2 hydrogens. I don't have enough hydrogens on this side. So what am I going to do? Let me go ahead and let's put a 2 here. So if I have 2 H2Os, now I have 4 H's, but I only have 2 oxygens. On this side, I have 3 H's and I have 1 oxygen. So I'm definitely going to be, I'm off. Let me come over here and let's put a 2. My lithium becomes 2. But my lithium on this side is still a 1. So let me go ahead and put a 2 on this side. Now my lithium is a 2. But let's look at the OHs. I have 2 OHs. So OH, OH, and 2 hydrogens. 1, 2, 3, 4 hydrogens. 1, 2, 3, 4 hydrogens. 1, 2 oxygens. 1, 2 oxygens. I am balanced. So I have, look at it this way, an OH and an OH, 2. An OH and an OH, 2. Hydrogen and hydrogen, 2. Hydrogen and hydrogen, 2. Am I balanced? Oops, 2 and 2, check. 2 and 2, check. 2 and 2, check. So this was a little trickier, and it was a little bit easier to actually break it down to each individual element or atom, so that way I can visually see it versus this way. Okay? That might help you out. It helped me out doing it that way. Let's go ahead and let's continue with our notes. We've got the types of chemical reactions. So we know that there's reactions that occur, but the reactions, when they occur, they actually have names. So the different type of compounds that are going to form from this, they have different names. So a reactant where atoms or ions actually transfer always has a single element on either the product or the reactant side of the equation, is what we call a redox reaction. Now the oxidation numbers of the elements, the oxidation number of the electrons lost or gained by an atom, right? The oxidation number, the +1, -1. Now it says here, look at the periodic table to find the oxidation number of the elements with predictable charges, meaning not the transition metals. You will have to calculate the oxidation numbers of the transition metals because they have more than one oxidation number. Number 1, free elements have an oxidation number of 0. Number 2, the sum of the oxidation numbers in a compound needs to be 0. So we'll come back and look at that a little bit later on. But let's go ahead and look at the type of redox reactions. We have 4 different types of redox. We've got a synthesis, I have a decomposition, I have a combustion and a single replacement. Oops. Now, let's go ahead and look at those individual redox reactions. All of those are going to be redox reactions. Okay? First one is synthesis. It says here it forms a single product from two or more reactants. So when I look at this, I have A plus B equals AB combined. Okay, so calcium oxide plus H2O water yields calcium hydroxide. Okay, now this is what we call, right, a skeleton equation. So let's double check to make sure it's balanced. I have calciums, I have oxygens, and I have hydrogens. Now 1 times 1 is 1. Oxygen 1 times 1 is 1. Hydrogen 1 times 2 is 2. Oxygen 1 times 1 is 1. This side, calcium 1 times 1 is 1. Hydroxide 1 times 2. Why am I saying 2? This 2 gets factored into here and over here to the H. So 1 times 2 is 2. 1 times 2 is 2. Am I balanced? Well, let's double check. 1 and 1, 2 and 2, 2 and 2. Yes, I am. You have the option to leave it alone or put a number 1 in front of it. Now let's look at the decomposition part. It says here that it's actually the opposite of the synthesis. It says that a single reactant breaks actually apart into two or more elements or new compounds, often requires an energy source. So in this case, I have A, B that are together already combined. The chemical reaction is going to take place, and now I have A's plus the B's separate. So let's go ahead and let's look at what a chemical reaction, skeleton equation, and balance looks like. So mercury 2 oxide, alrighty, mercury has a +2 charge. Oxygen is a nonmetal which has a -2 charge. Decomposes when heated. What does the word decompose mean? It means that it breaks apart. So that means that we're going to have mercury, and I'm going to have hydrogen separate. So let's write this in. Those two are going to crisscross, but it's a 2 and a 2. So what happens? They cancel each other out. So HGO arrow, Hg plus O. But wait a minute, oxygen's a diatomic. So let's put a little 2 behind it. Let's put Hg and O. Let's do our little walls and let's multiply. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. 1 times 2 is 2. I am not balanced. So if I come over here and I put a 2, 2 times 1 is 2. 2 times 1 is 2. My oxygens are good, but now my mercury's not. So come over here and put a 2. 2 times 1 is 2. Check it. 2, 2, 2, and 2. Now I'm good to go. Let's go ahead and turn the page to chemical combustion part. So it says here, any substance combining with oxygen is a chemical combustion. All products will have a oxygen in them. Energy is usually released in the form of heat or light because it is burning, right? The word combustion means to burn. So let's look at this. I am going to have, there we go. AB plus O, it's a diatomic, so put a 2 because it combines with oxygen, here it is, yields What does it yield? It yields some type of energy plus it yields O because the oxygen breaks apart plus BO. Okay, so let's look at a balanced equation regarding a combustion. These reactions usually produce a large amount of energy, but usually a catalyst is needed to start the reaction. So I have hydrogen and oxygen, H2O on this side. Let's go ahead and let's practice this one. Hydrogen and oxygen. Draw our wall. Let's multiply. 2 times 2 is 2. 1 times 2 is 2. Why did I do that? I apologize. 2 times 2 is 4. And 1 times 2 is 2. 2 times 2 is 4. 2 times 1 is 2. And look at that. 4 and 4. 2 and 2. I am balanced. And if you wanted to, you can put a number 1 here. You don't put a number 1 in front of that. That capital E stands for energy. Let's keep going. So the next part here is going to be a combustion reaction. It says here continued. So we're still talking about combustion reactions. Combustion of carbon and hydrogen compounds. Reactions commonly involving hydrocarbons, okay, which are compounds of hydrogen and carbon. Hydrocarbons always produce carbon dioxide and water. Okay, so it's still a combustion, but in the product, it's going to have carbon dioxide and water. Let's look at this one and let's make a skeleton equation. Hydrocarbons always produce, it says here, carbon dioxide and water. So C6H6, which is carbon and hydrogen, plus oxygen, because it's still a combustion, which must contain oxygen in the reactant side, yields, well, carbon dioxide and water. So what is carbon dioxide? That is CO2. Water is H2O. And then there's some type of energy form involved. Let's go ahead and write it out. I have carbons, I have hydrogens, and I have oxygens. Let's draw our wall. Let's multiply. 1 times 6 is 6. 1 times 6 is 6. 1 times 2 is 2. 1 times 1 is 1. 1 times 2 is 2. Hydrogens. 1 times 2 is 2, but oxygens, 1 times 1 is 1. Am I balanced? No, I'm not. So let's go ahead and let's keep going. What do I need to do? Well, on this side, I need more carbons. So to make more carbons, because there's a 1 times something is 6. 1 times 6 is 6. So 1 times 6 is 6, but wait a minute, on the oxygen, it's going to change it up. 6 times 2 is 12. 12 plus 1 is 13. Oh man, we're going back to those weird odd numbers again. Am I balanced? No. My carbons are good, my hydrogens are not, and my oxygens are just completely out of whack. But hydrogens, I have a 2. 2 times something equals 6. 2 times 3 equals 6. 3 times 1 is 3. So 12 plus 3 equals 15. Whoa, I'm getting bigger and my numbers are still odd. So my carbons are good, my hydrogens are good, my oxygens on this side are not good. So there is a number, if I multiply it by 2, to equal 15. What number do I need to multiply by 2 to equal 15? 7.5. I know, that's weird. Now, we cannot use a 7.5. Absolutely not. But 7.5 times 2 equals 15. Am I balanced? 6 and 6, 6 and 6, 15 and 15. I am balanced. But the problem here, though, is that that's a 7.5, and I cannot have a 7.5. So in that case, when you have a decimal in the place there, you multiply all of it times 2. So 2 times everything. 2 times, so this is a 1. 2 times 1 is 2. 2 times 7.5 is 15. 2 times 6 is 12. And 2 times 3 is 6. Now I'm balanced. Since I was already balanced and I had a decimal point, I don't have to recount, okay? You could if you want to, but you don't have to. And all I have to do is multiply everything by 2, okay? I know it's a weird one, but it's one. Let's keep going to single replacement. Atoms of one element replace with atoms of another element into a compound. Whether or not the reaction occurs depends on an activity series or reactivity of the elements. So, rule: metal replaces metal if it's more reactive. Most reactive metals, the most reactive metal that we have is lithium in group 1. Group 1 is more reactive than group 2 metals. For transition metals, though, the closer it is to lithium, the more reactive it is, okay? Now, nonmetals replace nonmetals if it's more reactive. Most reactive nonmetals is actually fluorine in group 7. And group 7 is more reactive than group 6. And the closer to the fluorine in group 7, the more reactive those nonmetals are. Okay? So let's go ahead and let's take a look at this. This is called single replacement. So on single replacement, I'm going to have, for an example, A plus BC yields AC plus B. Okay? So let's take a look. Now, the other thing too is I need to also, for an example, I can see that this is Ag, that's a metal. Metals have a positive oxidation. And B is going to be, let's look at that. I'm sorry, copper plus Ag, which is a metal again. NO3, which is a polyatomic negative charge. A on this side is a positive charge. And C on this side, because it's still the same C, the polyatomic, is a negative charge, and B is a positive charge. So what happens is this A is going to come over here. Because it's a metal, metals are going to replace metals. Non-metals replace non-metals. So this metal here, A, is going to kick B out of the way. Kick him out of the way. And look at that. AC now are together and B is by himself. This A cannot replace the C. Why? Because the C is a non-metal. Metals can only replace metals. So let's practice this. We have a few to practice. Okay, and a few to look at. So copper is going to kick silver out of the way and it's going to replace it. Now I have silver by itself and copper nitrate. Let's look at this one. On here I've got fluorine, and fluorine is a non-metal. Is it going to replace the sodium or the bromine? The bromine, because bromine is a non-metal. Now they didn't finish this, so let's go ahead and finish this. Bromine got kicked out, so he's by himself. Bromine plus Na, because sodium is a metal. Metals are written first. F. Okay? Now let's go ahead and let's look at this. Bromine is going to be polyatomic, a +2. Sodium, Na, and fluorine are going to cancel each other out from the periodic table due to their oxidation numbers, so that's what it should look like. Okay? And let's keep going. And just in case if you wanted to see it, Sodium Na is a +1 and fluorine's a -1. So they crisscross. That's the reason why it looks like that. Okay? Let's keep going. Wait a minute. Let's pause for a moment. These are skeleton reactions. Are they balanced? Let's double check. I've got fluorine, I have Na, and I have bromine. Draw my line. 1 times 2 is 2. 1 times 1 is 1. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. 1 times 1 is 1. I'm not balanced. So on this side, I need more fluorine. So I'm going to put a 2. Now, NAs. 2 times 1 is 2. Fluorine, 2 times 1 is 2. I'm not balanced. So on this side, NAs, I need more. So let's put a 2. 2 times 1 is 2. And my bromines, 2 times 1 is 2. Am I balanced? 2 and 2, 2 and 2, 2 and 2. Yes, I am balanced. The next one, aluminum metal reacts with copper to chloride. Okay, so let's go ahead and write that out. I've got copper 2, so I'm going to scoot over here and write it. Aluminum metal, Al, reacts with copper 2, Cu, chloride, Cl. 2 stands for a +2 charge. Chlorine is a nonmetal, which is a -2. I must crisscross those. So it should look like this. Al plus CuCl2. Okay, now the reaction is going to occur. The aluminum is going to take somebody's place. Is he going to take the copper or the chlorine? Metals can only kick out other metals. So aluminum is going to come over here and kick out the copper. And so copper is going to be by itself plus aluminum and chlorine. But wait a minute, aluminum is a metal, so he has a plus charge. He's in group 13. Chlorine is a nonmetal, which is a -1 charge. Crisscross those, so that's going to be a little 3 over here. Am I balanced? Well, let's check that out. Al, Cu, Cl. 1 times 1 is 1. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. 1 times 1 is 1. 1 times 3 is 3. Oh, yeah. 3. Whoa, I'm not balanced here. So let's go ahead and let's balance this. I need more chlorines over here. Now, I've got a 2 and I got a 1. Man, there's a problem because I have a 3 over here, and that's an odd number, that's an even number. But I do know that 2 times 3 is 6. So I could put a 2 here, and that would be 2 times 2 is 4. That's not going to help this come up. But if I put a 3, copper becomes 3 times 1 is 3. Chlorine becomes 3 times 2 is 6. On this side, copper needs to have a 3, so it can be balanced. 3 times 1 is 3. Aluminum, 1 times 1 is 1 still. And chlorine, 1 times 3 is 3. I'm not okay. I need more chlorine. 3 times what equals 6? 3 times 2 is 6. So let's count the aluminums. 2 times 1 is 2. Chlorine, 2 times 3 is 6. Am I balanced? My aluminums are not. I need 2 aluminums on the reactant side. So let's put a 2 here. 2 times 1 is 2. Let's check. 2 and 2, 3 and 3, 6 and 6. Ooh, I am balanced now. Don't forget, we always end up with that. We start off with a skeleton equation. We need to balance it. So let's go ahead and let's look at the next couple here, and then we get to the next one, which is double replacement. Zinc plus copper sulfate. Zinc is a metal, and it's going to kick out either copper or sulfate. So who is he going to kick out? He's going to kick out the copper because copper is also a metal. So it's going to look like this. Zinc plus copper, Cu, sulfate, SO4, yields, well, who's going to be kicked out by himself? Copper plus zinc sulfate. How's that? Not bad. Okay, so we need to look at this. Copper is one of those weird transition metals, but if I crisscross backwards, I see that this is going to be a -2 and this is a +2. How do I know? Because they crisscrossed and they canceled each other out. So when that happened, then in that case, that's a 2 and a 2. Look at this. There's a 1 here and there's a 1 here. But if I go and look at the polyatomic chart, sulfate is truly a -2 charge. Because of that, 1 and 1, that means that if this is a -2, that must have been a +2, and the two 2's cancel each other out. So let's look on this side then. Copper, and I have zinc sulfate, and I'm going to look at those. Zinc is by itself, copper. It looks like we're good. Go now, double check, and I'm going to highlight this because you need to go and look and balance it. But the equation looks good. The skeleton equation looks good. Chlorine plus Na, sodium nitrate, sodium and nitrogen. Wait a minute. Chlorine is a -1 because it's a non-metal. Sodium is a metal, which is a +1, and nitrogen is a -3. So that's where that little 3 comes from the crisscross. But wait a minute, chlorine is a non-metal. So who is he going to kick out? He's not going to kick out the Na because Na is a metal. Chlorine is going to kick out the nitrogen. Okay? So let's go ahead and let's write that out. Cl plus Na3N yields N by itself because the chlorine kicked the nitrogen out, plus Na because metals are written first, Cl. Okay? So let's look. Sodium Na is a +1 charge. Chlorine is a -1 charge. They crisscross out and cancel each other out. What do you need to do? This is our skeleton equation. I'm going to put a little arrow here also. You need to go back and balance it and make sure that it's okay. It may or may not be okay. Let's go ahead and let's go to the next one. The next one here is it says double replacement. So let's look at this double replacement. This one is, and I don't know why it says redox type number 5, double replacement. Let me go back, let me look. Please come over here and scratch that out. It's not a redox. Not a redox. Write that in. I apologize, that's there. So a double replacement is not a redox. Now there's 2 types of double replacements. We have acid-base and we have a precipitant reaction. Okay? Acid-base and a precipitant. So let's look at what double replacements do. On double replacements, we have, look at this, A and B's plus, look at those are different. They don't look like the A's and B's. Plus C and D's yields A and D's plus C and B. Now when it comes to double replacement, we actually end up with a metal and a non-metal. I end up with a metal and a non-metal. So what happens is the metals kick out the other metals, the non-metals kick out the non-metals. So A is my metal, D is a non-metal, right? C is a metal, B is a non-metal. Do you see how they swap partners? That's what happened here. So now when it comes to, it says the 2 types, which are the acid-base or the precipitant reaction. It says it starts with acid bases start with a hydrogen. We know that because we talked about acids already. As a reactant, and the products are actually going to be H2O and a salt. A precipitant reaction is a double replacement reaction where one of the products is a soluble salt and the other product is an insoluble salt. It says here though, in this case, you need to use the solubility chart to determine if the products are soluble or insoluble. Before we go any further, we need to know what those words soluble and insoluble mean. So I'm going to come over here and I'm going to soluble. If it's soluble, that means that it actually dissolves. It dissolved. It broke apart. Now, if it's insoluble, that means that it is a precipitant. Or it was a solid. It was insoluble. It was unable to dissolve. Okay? That is our solid. So let's look over here at a few examples, and then we have the last chart over here, and then we're done with our notes. So the next part over here, example number 1, NaS aqueous plus CdNO3, which is a polyatomic aqueous, so that means two liquids that are dissolved in water, yields CdS plus NaNO3. Step 1. Let's go back and let's double look at what's going on. This is my A, this is my B, this is my C, and this is my D. My A is a metal. That's my nonmetal. My CD is my metal. Oops, I didn't need to put a 1. I just meant to put a positive oxidation charge, right? Metals are positive. And NO3, go to your polyatomic chart, it's a negative. So the positive or the metals can go ahead and swap with other metals. So the CD becomes our C and B, which is a metal and a nonmetal, and my Na is my A, which is a metal, and my polyatomic, which is letter D, which is a nonmetal. Okay? Now, we're going to have to go ahead and we need to double check our stuff here, and we need to decide, well, what's going to happen? Because it says over here, in this case, you need to determine if your product is soluble or insoluble. Did it say